Some notes about gain, amplitude and decibels. Figure 1.24 on page 26 of the extract from Chapter 1 of the Cipriani and Giri text shows three graphs. One of an audio waveform without an amplitude envelope, one of an amplitude envelope, and a final graph of the audio waveform with the amplitude envelope applied. You can see in the two graphs of the audio waveform that the amplitude of the signal goes from -1 at the bottom to +1 at the top. The zero line in the middle of these graphs represents the 0 point through which an acoustic sound wave passes from positive pressure to negative pressure. Technically, this number range is what is known as a normalized floating point representation of an audio signal. The middle graph shows an amplitude envelope. This graph goes from 0 at the bottom to +1 at the top. To control the amplitude of the audio signal, we multiply it by the envelope signal. Multiplying by 0 sets it to 0 and turns the signal off. Multiplying by 1 brings the full signal back. Here is a max patch that demonstrates multiplication of a signal. Notice that this multiply object has a tilde in its name. This indicates that it is one of the objects that handles audio signals carried by the stripy patch cords. You might be used to the idea that audio amplitude and gain are measured in decibels. How do we get from this 0 to 1 range to gain in decibels? The formula includes logarithms. A logarithm is the inverse of an exponent or power. We can find the power to which a given number has been raised to achieve a resultant change in level by applying a logarithm. For dBs, we use the number 10 as the base, which is raised to a power to achieve a given change in level. That power multiplied by 20 is the level change in dB, or decibels. For example, to find the dB difference of an increase in level by a factor of 2, say, from an amplitude of 0.5 to 1, we make the following calculation: 20 times the base 10 log of 2. Here, in the calculator, we find the base 10 log of 2, then multiply by 20. The result is close to 6 dB, which represents a doubling in level. You don't really need to worry too much about the maths, because computers are good at maths. In Max, we can do the same calculation using the A to dB object. There's a partner object called dB to A. Notice how -6 is equal to about 0.5. The useful thing about dBs is that each stage of gain in a system can be added or subtracted to provide the overall gain of the system. Some useful rough rule of thumb ratios to remember are 1 times equals 0 dB or no change, 2 times equals 6 dB, 3.2 times equals 10 dB, 10 times equals 20 dB, 100 times equals 40 dB, and 1,000 times equals 60 dB. That's the maximum gain on many mic amps. Notice how the exponents of 10 go up by 20 dB. That's because we're using the base 10 logarithm for dBs. Those ratios are all multiplying to give gain. If we reduce the level by dividing or multiplying by a fraction, we get negative gain, or reduction in level. 0.5 times equals -6 dB. 0.3 times equals -10 dB. 0.1 times equals -20 dB. If you want to know more, an excellent reference is provided on the University of New South Wales School of Physics site, PhysClips. Here's the URL. I hope that gives you some insight into the use of decibels and ratios and their role in gain in audio systems.